So some of the properties of a sphere, okay, first we have the volume. So the volume is equal to, this is 4 over 3 divided by pi, the radius of the sphere is to 3, that is for the volume. Then we have for the surface area. So surface area of a sphere, let's say SA is equal to, this is 4 pi, the radius, okay, squared. So let's have an example. Okay, so for our first example, we have a sphere with a radius of 3 centimeters. We are required to compute for the volume and the surface area. So we have letter A. For the volume, this is equal to 4 over 3 of pi, the radius cube. So we have the volume is equal to 4 over 3 pi. We have the radius equal to 3 centimeters. This is 3 raised to 3. So we may cancel one of the 3. So this is the same as 3 squared. Okay, so what is 3 squared? That is 9 times 4. 4 times 9 is 36. So we have the volume is equal to 36 of pi. This is now in terms of the cubic centimeters. Okay, that is for the volume. Then for the third B, we have for the surface area. The surface area of a sphere is equal to 4 pi divided by the radius squared. So surface area is equal to 4 pi. What is the radius of the sphere? This is 3 squared. So we have a surface area is now equal to, I think this is the same. We have 36 pi, but it will be square centimeters. So this will be our first example. So let's have more examples. Let's have another examples for spheres. So two spherical balls. So one 8 centimeters in diameter and the other is 5 centimeters in diameter is placed inside a cylindrical jar. So how to compute for the volume of a cylinder? So the volume is equal to, this is area times the height, or the volume is equal to pi, let's say RC, the radius of the cylinder, squared times the height. So compute the volume of water necessary to cover them. We are placing two different spheres inside a jar with a 10 centimeters diameter. So we are looking for the volume of water necessary to cover both spheres. So we are looking for this volume of water. So the volume of water, how do we compute for that? So the volume of water is basically equal to the volume of the cylinder minus the volume of, let's say, DS1, the volume of sphere number 1, minus volume sub 2, that is the volume of sphere number 2. So again, how do we compute for the volume of water? That is the volume of the cylinder up to this height, okay, minus the volume of the sphere number 1 minus the volume of sphere number 2. But we need to determine this h. So we have the diameters of the sphere. So diameter number 1 is equal to, so I place D1 for the smaller sphere. That is 5 centimeters, which means the radius is half of 5. This is 2.5 centimeters. Diameter number 2 is 8 centimeters. So we have radius number 2 is 4 centimeters. So how do we compute for h? So as you can see, this is the same as radius number 1. This is the same as radius number 2. We just don't know what is this height. We need to determine this dimension. How do we determine this dimension? Let's say this is y. All we have to do is connect the centers of the sphere. So this distance is the same as R1 and R sub 2. Do we know this horizontal distance? That is the same as 10 minus R1 minus R2. That is the same as 10 minus 2.5 minus 4. So that is the same as 10 minus 6.5. What is 10 minus 6.5? This is 3.5. So it is the same that we have this triangular portion. We have this y. This distance is R1 plus R2. Well, this distance, horizontal distance or center to center distance, horizontal for the two spheres. That is, again, 10 minus 2.5 minus 4. This is 3.5. What is R1 plus R2? That is 2.5 plus 4. We have this as 6.5 centimeters. So how do we compute for y? That is by Pythagorean theorem. So we have that as 6.5 squared equal to, this is 3.5 squared plus, we have plus y squared. So let us compute for the value of y. So that is the same as 6.5 squared minus 3.5 squared. Then square root. So we have it as the square root of 30. Okay, so square root of 30 centimeters. How do we compute for h? So we have now the value of h is the same as R2 plus y plus R1. So it's the same as R sub 2 plus y plus R sub 1. So we have h, R2 is 4. Y is the square root of 30 plus R1 is 2.5. So we have now the h. We have 4 plus 2.5 plus the square root of 30. Let's have it as 11.977 centimeters. So again, how do we compute for the volume of the water? The volume of water is equal to, what is the volume of the cylinder? That is pi. What is the radius of the cylinder? If it has a diameter of 10 centimeters, the radius of the cylinder is over 5 cm. That is, we have the volume of the cylinder is pi. We have 5 centimeters squared times the height to which we are going to build water. That is 11.977 minus volume of sphere number 1. That is 4 pi over 3. The radius of sphere number 1 is equal to 2.5. This is raised to 3. Minus the volume of sphere number 2. That is 4 pi over 3. The radius of sphere number 2 is 4 raised to 3. So this will be the volume of water to cover both spheres. So we have pi, 5 squared, divided by 11.977 less 4 pi over 3 of 2.5 cube minus 4 pi over 3 of 4 cube. So the volume of the water will be equal to 607.139. This is in terms of cubic centimeters. Okay, this will be our answer. Okay, next, so let us discuss the shapes formed from a sphere. So for example, originally this is a sphere. Then if we are to remove this portion, so the remaining will be a spherical segment. This portion is called as the segment, but this surface, the surface is called as the zone. So we have a cone, then a spherical segment, but the surface is called as the zone. So how do we compute for the volume of a spherical sector? So the volume is, take note, a spherical sector or a spherical cone is a pointed solid. If we say pointed solid, the volume is 1/3 of its base area multiplied by its okay, altitude. So what is that area? This time, this area is the same as the area of the zone. That is the area of, this is a curved surface, which is the area of the zone. Area of the zone is equal to 2 pi, and the radius of the sphere multiplied by h. So take note that our small h, and this small h is the height of the zone. Alright, so that's the height of the zone. So that will be our base area this time. If you are to observe this one, this is the altitude. Okay, the altitude of this spherical sector. But if you are to observe this distance up to this point, from the center of the sphere to the surface of the sphere, is the same as the radius. Alright, take note that the altitude of a spherical sector is the same as the radius of the sphere. So if you have to simplify, we have now the volume is the same as 1/3. What is our base area? That is the area of the zone. We have that as 2 pi, the radius of the sphere, the height of the zone. Then multiplied by the altitude, but the altitude this time is the same as the radius of the sphere. So if you have to simplify the equation, this is the same as 2/3 pi, the radius of the sphere squared multiplied by the height of the zone. So this is the simplified formula for the volume of a spherical sector. So take note that we have another r this time. Another r, let's have small r, that is the radius of the spherical zone. Alright, so if you are to remove this cone, alright, if you are to remove the cone from the spherical sector, it will appear like this. We have it as the spherical segment. Alright, so that will be our spherical segment. Just removing the cone from the spherical sector, we have the spherical segment. The volume of a spherical segment is basically equal to the volume of the spherical sector minus the volume of the cone. If you have to imagine, for example, if you have to remove this cone, okay, the remaining will be the spherical segment. So if you are to derive that equation, it will take long for the derivation. We can have it as the volume of the spherical segment as a pi multiplied by I. We need the height of the spherical zone. This is h. That is pi h squared. This is divided by 3 multiplied by 3 times the radius of the sphere minus the height of the spherical zone. So this will be the volume of the spherical segment. So let's have examples for the volume of a sector and the volume of a spherical segment. Okay, so let's have an example. So find the volume of a spherical cone and its spherical segment in a sphere of radius, so 19 centimeters. If the radius of its zone is equal to 8 centimeters. So we are looking for the volume of the spherical cone or the spherical sector and the volume of the spherical segment. As you can see, we have, if we are to compute for the volume of the spherical sector, or the spherical cone, we can have the volume equal to the 2/3 of pi, the radius of the sphere squared times the height of the zone. As you can see, we don't have yet the height of the zone. So this is, we don't have yet h, or the value of h. How do we compute for that value? But if you are to observe, what is this distance? That is from the point of the surface of a sphere towards the center of the sphere. Let's say this is point O, the center of the sphere. So basically, that is the altitude. But again, for a spherical cone or spherical sector, the altitude is the same as the radius. So what is this distance? If you are to consider from the center of the base of the zone to the center of the sphere, that is the same as, this is the radius minus, what is this distance? That is the height of the zone, h. So this is r minus h, and this is the radius. From the center to the surface is the radius. If we are to isolate this triangle, so we have this radius as 17. This distance is r minus h. This is the radius of the zone equal to 8 centimeters. So we can have it by Pythagorean theorem. That is the hypotenuse r equal to, we have the small r squared plus this value r minus h squared. So we substitute what is r. The radius of the sphere is 17 squared. The radius of the zone is equal to 8 squared plus the radius of the sphere is 17 minus h quantity I squared. 17 squared is 289 equal to 64 plus, when we expand this one, this is the same as 289 minus, so 17 times negative h, then I think you're twice that value. Negative 34 of h plus the h squared. So therefore, we can remove 289. So we have a quadratic equation. This is the same as h squared minus 34 of h plus 64 equal to 0. So we'll be having two values of h. We can compute them using the quadratic formula. So the quadratic formula for the roots equal to negative b plus or minus the square root of b squared minus 4ac. This is all over twice the value of a. So let us determine the roots using that equation. So we have one of the root is equal to 32. And the other root is 2. So which among them is the answer or the more realistic value of h? So are we going to use 32? So take note, this r or this height is only 17, so it is impossible to have a value of 32. Therefore, we have, this is the other root. We are using 2 as the height of the spherical zone. So 2 centimeters as the height of the spherical zone. So we can now have the volume. The volume of the spherical sector is equal to 2 over 3 pi times the radius. We have that as 17 squared multiplied by the height of the spherical zone. Okay, it is computed as 2 centimeters. This is multiplied by 2. So the volume of the spherical sector, so we have that as 2 over 3 pi multiplied by 17 squared multiplied by 2. So this is equal to 1156 over 3 of pi. This is in terms of cubic centimeters. So this is the volume of the spherical cone or the spherical sector. What about the volume of the spherical segment? So the volume of the spherical segment, so for the spherical segment, we have the volume is equal to pi h squared divided by 3 multiplied by 3 times the radius of the sphere minus the height of the zone. We have the volume is equal to pi. We have h is again 2 centimeters. This is 2 squared divided by 3 multiplied by 3 times the radius of the sphere is 17 minus the height of the zone is 2 centimeters. So this is the volume of the spherical segment. that is pi 2 squared over 3. We move it by 3 times 17 minus 2. So we have it as 196 over 3 pi, this is cubic centimeters. So this will be our answers, the volume of the spherical sector and the volume of the spherical segment. Okay, so let's have another solid formed from a sphere. We have the spherical wedge. So one basic example of a spherical wedge is one slice of watermelon. Okay, so since it is just a portion of a sphere, we can compute the volume by ratio and proportion to that volume of a sphere. So it has corresponding, let's say, a central angle theta extended by the radius of the given sphere. So let's have the volume of a wedge or a spherical wedge corresponds to a central angle theta is equal to, let's have the volume of a sphere. So if you say sphere that is complete, its central angle is by one rotation 2 pi or 360 degrees. So if you are to compute for the volume of a wedge, that is the ratio of theta over 2 pi multiplied by the volume of a sphere. The volume of the wedge is equal to theta over 2 pi, while the volume of a sphere, that is 4 pi, divided by 3, the radius raised to 3. So we may cancel 4 pi, 2 pi, so this is the same as 2. So we have the volume of a spherical wedge is the same as 2. This is over 3. Multiplied by theta, your theta should be in terms of radian, multiplied by the radius of the wedge cube, or the radius of the sphere cube. So this is our formula for the volume of a spherical wedge. So what about the surface? Okay, how do we compute for this surface? So this surface is known to be or called the lune, since it is in the shape of, let's say, first quarter of the moon. Okay, the area of the lune. So how do we compute for the area of the lune? So the area of the lune, we can have it by ratio and proportion again with the sphere. The area of a lune corresponds to a central angle theta is equal to the surface area of a sphere. Again, if we say a sphere that is complete with a central angle equal to 2 pi. So we have the area of a lune is equal to theta divided by 2 pi multiplied by the surface area of a sphere. So we have it as theta divided by 2 pi. What is the surface area of a sphere? That is 4 pi r squared. So we can cancel by 4 pi and 2 pi. This is the same as 2. So the formula for the area of the lune is equal to 2. Your central angle should be in radians multiplied by the radius of the sphere squared. So this will be our formula. That is the formula of the surface. We call it the lune. Let's have examples. For example, we have this spherical wedge with let's say the radius of the sphere is equal to 3 centimeters, and the central angle for this wedge is equal to 30 degrees. Or we are required to compute for the volume and the area of the lune. So we have it as letter A, the volume of a spherical wedge is equal to 2 over 3. This is theta radians multiplied by the radius cube. So we have the volume is equal to 2 over 3. Our central angle is 30 degrees. We are to express this one in radian multiplied by pi divided by 180 degrees. Then multiplied by the radius cube. This is 3 centimeters raised to 3. So let's have the volume. The volume is equal to 2 over 3 of 30 degrees, expressing that one in radian multiplied by pi over 180. Then the radius 3 raised to 3. So you have the volume is going to equal to 3 pi cubic centimeters. Then computing for the area of the lune. So we have letter B, the area of the lune is equal to 2 theta radians multiplied by the radius squared. So we have it as twice of 30 degrees times pi divided by 180 degrees to be in radian multiplied by the radius, that is 3 centimeters squared. So we have it as 2 times 30 of pi over 180 multiplied by 3 squared. So this is the same as this is 3 pi square centimeters. So this will be the area of the lune.